Next up is Tamu. Floor is yours.
Hi everyone. Today I will present our end-to-end flow to integrate and generate custom RISC-V ISA extensions. And the problem that we are facing is that the design is really hard and core specific, and especially in the domain of RISC-V we have plenty of open source cores available and might want to try different ones. So we have developed an end-to-end flow with the goal to make it more accessible and portable. And for doing so, we start with a core DSL description of the extension, which is a high-level description language specifically tailored for this purpose. And as the next step, we leverage high-level synthesis that generates the very core-specific system Verilog RTL code, which is then integrated into an existing core we use for this RISC-V that can generate an ISA specific interface that is very lightweight and specific for this extension. And finally, we obtain our base core together with the extension and can use it to accelerate our workloads. And a nice thing about this approach, especially with the high-level synthesis part, is that we can use the same input description and use it to try out different cores. And that is what I will demonstrate next. Okay, that's a bit small. So let's say you used RISC or another tool to profile your workload and found out that that your computations of square root are very slow, and you might want to express it in a custom extension to speed up your workload. Then you could write a core DSL file, which you can see on the right-hand side. That looks very familiar to see, so it has a high abstraction level, with the key difference that you have to specify certain things like encoding for the instruction or the signedness and bit widths of the values. But apart from that, you can still use loops and if-else blocks and so on. So you have a really high abstraction level and can write extensions really fast. Additionally, you can also use more complex features like manipulation of the program counter, memory accesses, read-writes, and so on. And you can even add custom registers, or in this case, ROMs, so read-only memory, and use it for some cryptography if you just want to try out some new ideas that you have. It's really fast to implement it in core DSL. So for our tool flow, we are using, 1 second please. For our tool flow, we are using a kconfig-based interface, which makes it really easy and familiar for at least Linux users to use. We have a few open source cores available to choose from. So for this demo, we will start with CVA5, and we can choose several extensions. Of course, we want to use our square root extensions, and we also have a few other ones lying around. We could just integrate them because we can. We have some HLS configurations, which I won't have time to go into, but maybe you can ask me later for that. And we also have the option to simulate the whole core with the extension and run a test program, which I will show at a later point. But for now, I will just generate the extended core. So let me save this config, zoom in a bit. And then I can type, obviously. So we can just run make build. And we should get an output folder here that has the CVA5 core source code, which was wrapped to contain the ISAs, which also is present in this folder. So now we can do the same thing, but with a different core. An example for Orca. Again, we have to save it. Oops. And run make again, and then we'll get another folder that contains a different core, the same ISAs, which is slightly different in the implementation to suit the new processor, but we still obtain a fully working processor that has our custom instructions. So, as next part of the demonstration, I want to show the simulation capabilities that we already have. Let me just zoom in a bit. So again, we have CUA5, all extensions, and this time we have the simulation part enabled. And there we can specify a C++ program that will be run on the extended core, and a file that contains the expected results from the execution. So if we save this again and run our magic build command, it should run a CocoaDB simulation and execute the test bench that I have opened here on the right-hand side, where we have again a software implementation of the square root. We have intrinsic support for our custom instruction, and simply compare the results and write it back in a result data vector, which is expected obviously to be 0, such that the software implementation corresponds to the extension and our custom instruction. And as you can see, the test passed, so at least we had luck here and no crashes during a live demo, which isn't obvious. And again, we can do the same thing. We had the CUA5 and Orca already, but we can also run this on a Pico RV32, for example. Save again, run make, and then it should hopefully pass. Yeah, as I already mentioned, we have intrinsic support, which is also automatically generated for the ISAs that we pass in, but we don't have pattern selection or something like that. It's just basic assembly and intrinsic support, but which is sufficient for some basic tests and also for small applications. And as you can see, also for a different core, it passed as well, and it's quite usable already. So that's my demo so far, and if you have any questions, I'm very happy to answer them.
Thank you, and we have a little bit of time for questions while we set up the next one, so keep them coming.
Is it in scope for the project to go beyond the intrinsic support and have like automatic recognition of?
Yeah, as you can see there, we are part of the Scale for Edge project, and other partners are working on that. So yeah, there's definitely work going in that direction.
There has been a poster from the TU Munich about auto-vectorization of LLVM. This is a co-located effort with this one.
Sorry, more questions? Some more questions. Then, thank you again, Tamo.
Thank you very much.